vector in the plane, then it is orthogonal to our guy. Okay, we should call this another letter. We should call this U. Okay, so I want to draw in what one of these guys U could look like. Okay, so in our diagram, U is orthogonal to the norm. Okay, and the proof of this is really nice. It's a really nice, like, slick algebra thing. So we say U dot n is following guy. Now we can split up, we can bring the dot product across this minus sign. And now we've got something equal to C minus something equals to C, which is 0. Right, so if we go from the origin to a point in the plane, not necessarily orthogonal. If we go inside the plane, if we go a vector inside the plane, we get something that is orthogonal. Comments there, observations there. For the fellow who asked the question, does this help at all? Okay, it helps a little bit. Okay, cool, good, good. Progress is being made. Okay, so ponder that, think about that. Very, very good example. Now we'll sort of head in the direction of functions of several variables. We've got one of these planes. This gives us some kind of relationship that X, Y, and Z need to satisfy. Right? This is an implicit definition of the plane. X, Y, and Z have to satisfy this equation. Right? This gives a function of two variables. Usually we let Z be our dependent variable. So we can think of this as being function that takes two inputs and returns our z as our output. So what that formula is saying is at the point xy, output the height z. So we usually graph these things the following convention, so that x is increasing in this direction, y is increasing in this direction, and z is up. Okay, we usually think of z as pointing upwards, out of the plane. Okay, so there's 1 point on our graph. So we get that point by plugging in x is 0, y is 0, then we get 4/3 here. If we plug in x is equal to 4, y is 0, we get a 0. And if we plug in y is equal to 2, you can cancel out that 4. Something like this. So those are our x-intercept, y-intercept, z-intercept, and we get some kind of a plane. So now we'll do a graph that a parabola by hand. So graphing things in 3D, generally quite difficult. We'll try our best on this though. Now our table of values is going to have two inputs, x and y. And we can, actually this will all give the exact same value. We'll make these 2's. Okay, so we plug those into our function. This is exactly the kind of thing mathematicians invented computers to do for us. Don't let the computer scientists forget that. Mathematicians came first. In any case, we make our table of values. We can imagine we've got the origin here. As we move along this direction, All right, we go up 1 unit. Okay, now as we move along X direction further, we go up 2 units. Or sorry, we go 2 units in the X direction, 4 units in the Z direction. Something like this. This is about the sketch that we get from the points that we have when we play connect the dots. You see that we're going up like this. And a little bit of reasoning suggests that this will be constant on any circle we draw, right? Any circle will have x squared plus y squared as a constant. So we'll get circles. So as you can see, even from this one example, it's hard to get the perspective right. On the midterm, you'll be asked to label points. Okay, so the grader has some chance of interpreting your sketch. It'll say label 4 points or label 5 points. Okay, so you'll make up 5 points, calculate the values, label them on your sketch, get good marks. Yes.
If we get something similar to that kind of equation, let's just say like we kind of like botch the drawing, would we still get full marks?
Yeah. Oh, sorry. Assuming that you label everything correctly.
Oh, okay.
So if you kind of, you sort of do a little bit of this kind of thing, as long as you label points, you're good. So you label full marks. This isn't Bob Ross painting class. This is math.
And how would you also distinguish like a point that has both x, y, and z?
Aha, right. So, sorry, here we've got our x, y, and z. Are you?
Yeah, like how about, you know how like it looks like it's like you just treat them as like different like coordinates? How about there's like all 3, like x, y, and z are not 0? How would a point look like?
1, 2, 3, like.
Yeah, like
Oh,
1, 2,
right.
3.
So yeah, like there's a point on here, half.
Yeah.
Half? Half? That's on
Yeah.
there? Yeah, so, yes. Right, so you come out into this xy plane. Or here, let's look at what happens at 1, 1. Got 1, 1. Right. So to plot 1, 1, you come out onto this plane and then go up the appropriate height.
Oh, okay.
Okay, so that's one way of interpreting these things. Now I want to talk about that sort of mountain climbing topographic maps way. So when we were looking at that map of the countryside, right, we saw that it was cut by equal heights. Okay? These equal heights are what are called level curves. Okay, so the level curve is the set of all x and y's that output the same value k. Okay, so it's all the outputs, sorry, no. It is all the inputs so that f outputs k. Another way to think of it is all the places on your mountain range of height k.